All right, there we go. A little bit. You can actually see me instead of being a black silhouette. But welcome back. I hope you did well or feel like you've been successful on your mid-unit assessment. We are going to tack on a few new vocabulary terms and build our understanding of trigonometric functions regarding the midline and amplitude. So we can describe graphically how the functions are being transformed. So once again, a unit we've already discussed and are simply applying in a different context. And I'll know I've got it when I can write a trigonometric function to represent situations with different amplitudes and midlines. We have midline amplitude. It is a topic that can get a little uncomfortable, so I'm going to give you the preliminary definitions of the both. The midline is given by the average of the maximum and minimum values taken by the function, while the amplitude is the length between the maximum value and the midline, or equivalently the length between the midline and the minimum value. All right. So the midline basically is that value that makes that the function is symmetrical over. And the amplitude simply measures the distance between that line and the maximum or minimum value. So let's get into it. Match each equation to its graph. What is one strategy used to match the graph with an equation? All right. It's been a while since we've talked about function transformation. So just giving you an opportunity here to refresh your memory. As you can see, we have parabolic functions all around. Sorry, my allergies are like awful right now. Parabolic functions all around with different types of function transformation. So while, yes, obviously you want to make sure that you correctly identify them, right? I'll start you there with that's y equals x squared. Okay, take a look as you are matching up your graphs to both algebraically what is changing for each function and visually what is changing if this is a topic that you seem to have forgotten. Like I told you before, function transformation is timeless, for lack of a better word. All functions can be transformed, and those transformations do the same thing. So if you add a constant to a linear, parabolic, cubic, polynomial, exponential, logarithmic, trigonometric, the function will raise up in height. Subsequently, if you subtract, it'll lower in height. So this is definitely a topic that you want to make sure that you are comprehensive about. All right, so let's say we have a windmill with a radius of 1 meter. The center of the windmill is 0, 0 on a coordinate grid. Boop. Write a function describing the relationship between the height, h of w, and the angle of rotation, theta. Explain your reasoning. Think about what it means if we are trying to, and this really should say, oops. All right, so we're looking to write a function in terms of h that describes the height of the point. You have two, well, technically three, sine, cosine, and tangent. Which one of those functions conveys a vertical quality? In this case, the height. All right, after you do that, describe how your function or in its graph would change if the windmill blade has length 3 meters or a length of 0.5 meters. In this graph here, you're provided with all three of those functions. Describe the difference that you see between the graphs and think through which color represents which graph. By this point, you should know. For these types of functions, the parameter k in the equations, right? So k cosine theta, k sine theta. So that's a scale factor. Changes the height of each graph by a factor of k, and the absolute value is called the amplitude. As I had said before, the amplitude is going to be that distance between, and obviously all three of these are going to have a midline of the x-axis or y equals 0. So the distance between y equals 0 and the maximum or minimum values here. All right, so here in this situation, we have a windmill, radius 1 meter, but the center is now 8 meters off the ground. As compared to the last activity, right? It's kind of theoretically impossible for the center of a windmill to have a center of 0, 0 because obviously it has some height. The point W starts at the tip of the blade in the position farthest to the right. It rotates counterclockwise. So we're not changing anything except for the initial height of the function. Once again, create a function that describes the relationship between height, h of w in meters, and the angle theta of rotation, right? So whatever your trig function is, you need to have an input of theta, since that's what da-da-da. After that, we'll explain our thinking. Here you'll take your function, enter it into the graph, see how it's behaving, and how does that compare to the graph where the center of a windmill is at 0, 0. So if you want, you could even go ahead. This graph will not take theta as an input. So if you're going to say cosine, it's going to have to be cosine of x. And for all intents and purposes, just delete that part. Right? So keep that in mind. As I said before earlier in this video, the visual center of the graph is called the midline. What would the graph look like if the center of the windmill were 11 meters off the ground? Explain how you know. And obviously, you can go back to the previous slide and work it out so you can see what's unfolding visually. And what value would you say is the middle value for the outputs of this function being this one here, where the center is 11 meters off the ground. And that's where we're going to pause, ladies and gentlemen. So like I said before, we're simply just taking an old concept and applying it to a new context. Yes, technically it's new, but technically it's old. But if you have any questions, we'll pick up together in class.